Hello, hey, we are working on Euler's method today. Yes, that's how you say it, not Euler, but Euler. And Euler's method's kind of fun. It's not very difficult, and it is an approximation method, kind of like linear approximation was, only this is a more accurate approximation method. So, what's the gist behind this? Um, what you're seeing on the screen is a little bit of just narration of what is going on. It says for differential equations that cannot be solved, a slope field is often used. It's the graphical representation of the original function if we can draw in that trend line. And then the problem with that method is the slope field's only really good for getting general trends in the solutions and the long-term behavior. There are times when we need something a little more accurate. Maybe we need to determine how a specific solution behaves, including some values that the solution will take. So we come in with the numerical methods that allow us to do that. Should see something about tangent line approximations. That's the linear approximation method that we've used before, where we look at y minus y1 equals the slope of x sub 1 times x minus x sub 1. And then I can bring this y1 over to the other side and get y is about y1 plus all that stuff. Put it in there. Yeah, so we've done linear approximation methods. It's basically an application of the tangent line. And that method, if we continue to repeat it, like if we continue to upgrade it, changing the tangent line just ever so slightly, we can kind of tightrope walk ourselves out to a better approximation. Yeah, the process is pretty easy and it's very repetitive. You're going to see that. So this up here, this graphic that I have up here, I wanted to talk about that for a moment. So the blue line is our curve, our original curve. And if I wanted to get an approximation where I knew my starting value of x sub 0, and it would give me I know my x sub 0 and y sub 0 points are numbers, then I could write the equation of the tangent line. Let's say we also are able to know what the derivative is. So we could write that original tangent line. And you can see if I were trying to approximate, let's say we're trying to head out here to x sub 4 and find the y value that corresponds with x sub 4. Well, if I extended my tangent line, just trying to follow, oh, that's terrible. Running this line out, trying to follow that slope of the first segment, you could see I would be quite a ways off by the time I get out to x4. But if I stopped and recalculated at a change of x over to get me to x sub 1, and I recalibrated my tangent line, so rewrote it, recalculated the slope, and I knew my x1, y1 point, well, now I get a new tangent line, okay? That one's going to be better as I head over to x sub 4. But maybe I continue to upgrade, let's get an x sub 2 down here, upgrade this tangent line as I move out. And so at x sub 2, I get a new slope. Oh, it's even getting better out here at x sub 4, right? And then maybe I do it one more time where I get x sub 3 and I upgrade that tangent line one more time. And there's where I'm going to claim that I've got x sub 4, y sub 4, some value. And I can get the y value for it. This y value is a whole lot closer than any of those other tangent lines would be. So it's this approximation method where I continually kind of make upgrades to the process. And you notice how this kind of started mimicking the curve. So that's what we're going to do. As you can guess, that delta x, we're going to keep it pretty small so that this is changing. Let me clear the ink on this. Move me. Change the ink. What if, I might have this locked. Oh, I do. Hey, let's unlock this. If this were very small, little change of x's, you can see how over a little space of time, it's really going to hug the curve nicely. All right, so down below, this is how I used to teach it. I've got easier. I mean, you can memorize the chart, but there's a little bit easier method. And we're just going to play off of this idea of the equation of the tangent line. So, oh, that moved. Let's start off with the idea that we have the equation of the tangent line, and we're all very proficient at doing the equation of the tangent line, right? I'm indicating here that I have a derivative based on x and y values. It could just be one or both of the variables. And then I'm going to take and just kind of reclassify some of those numbers. So instead of y sub 1, which is my ordered pair that I kind of began with, I'm going to call that y sub old and x sub old. So that as we move through this, that was the old pairing, and then now I'm going to come in with a new xy. So remember that curve that we had, here was my original point, x1, y1. Then I moved over a little bit, and I came in with a new x1, y1. But I'm going to call those my old values till I get the new values, okay? So that's the reference on the old. That ain't working. So then next, what's my next update? Oh, linear approximation is what I'm trying to illustrate on this next modification. So just a little bit of algebra. I'm moving this over to the right side of my equation. So I'm going to have y sub old plus this stuff. F prime, the slope, times the difference in the x's. Oh, and difference of the x's, when I say that, here is that update. So I'm taking now y minus y old has a difference, and I'm calling it delta x. So I end up with delta x times the slope, and I'm suggesting that that could be thought of as delta y. Why would that be? Well, think about slope. Let's just go back to 7th grade. And your teacher told you the slope was equal to the change of y's over the change of x's. And then we got into Calc AB, and we kind of found a new way of getting slope precisely at a point, and we called it our f prime, didn't we? So this was, f prime was basically our slope, only over very, very small quantities, very, very small change of x. What happens if I multiply both sides by a delta x? Well, I get that delta x times the slope calculated is our change of y. So that's where this is coming in. I'm saying the change of x times the slope will leave us a delta y. Now, I can get a new y by taking y sub old plus y sub new. Or change of y. I should say change of y. Yeah, that's Euler's method. This last line is essentially what we're doing for Euler's method. And we're doing it repeatedly because we're walking our way from x sub 1 out to maybe x sub 4. Maybe we're taking 4 steps to get out there. Or maybe we're taking 2. Hopefully fewer steps because it's a little less work. So let's look at example 1. Given the differential equation, they give us the derivative, dy dx is equal to x minus 2. Notice it's only in the variable of x, so that's kind of nice. We have an originating point. We're going to start at 0, 5, aren't we? This is our starting point. Sweet. Now it says find an approximation for y of 0.8 by using Euler's method with 2 steps. Oh, and they're equal. Sketch your solution. So there's a few things I want to do. I'm going to kind of lay this out. Here's how I kind of do my columns. So I'm going to have XY. Then I'm going to say that my Y old plus my slope, you know what, I'm going to do delta X next because that's usually how I lay it out. The change of X and then times the change or the derivative evaluated at XY, which that'll be the one place where we actually have to make some calculations. That when added together gives me my new updated Y value. Okay, so that's kind of my chart that I design, and it's nothing more than tangent lines equation. So we want to get to 0.8, and I'm starting at an X value. We're starting at 0.5, correct? I want to get down here to a 0.8 for my X value. And I'm doing that in 2 steps. So my change in X is going to be where I finished minus where I began, done in 2 steps. That means my delta X has to be 0.4, correct? So I would have one more stopping point here at 0, then 0.4, and I'm going to have to find that Y value. And then I'm going to do another delta X of 0. Bringing me to 0.8. All right, sweet. So Y old, I'm starting with 5. I'm going to add to that some change in Y. That change in Y is going to be calculated by going delta X times the change in the slope of the derivative. So delta X is 0.4. We calculated it over there, and that's going to stay consistent, and it has to stay consistent here for Euler's method. Now, really, here's the only work I've got to do. I've got to calculate my f prime, and remember that f prime and dy dx being the same thing. So I'm going to put in my x value of 0, take away 2, and that's going to end up being what? 5 minus 0.8. Because 0.4 times 2 would give me 0.8. It's negative. So I get 5 minus that. That's going to get me a new y value of 4.2. Sweet. I'm going to come down now. So there's kind of my first calculation. I'm coming down. My updated y value gets me to the point of 0.4, 4.2. Back through the process. Now my old y value, I'm picking up from 4.2, adding to it, change of x times, and I got to recalculate the slope at this. I'm creating kind of that new tangent line equation. So I'm going to put in what? 0.4 minus 2, which gives me 0.4. 2 minus that would be a 1.6. And hopefully, hey, most of the time, these are calculator active, and you can see why. So I'm going to end up with 0.4 times 1.6, which gives me 0.64. And I'm just looking at my equation here because I missed the 4.2 in the beginning, right? But this is equal to 4.2 minus 0.64 is what that calculated out as. And that is 4.2 take away the 0.64 gets me 3.56. There's my new y value. New y value goes right here, 3.56. I don't have to do any more calculations because when x is 0.8, my approximation for y is 3.56. Find the approximation. Y of 0.8 is approximately 3.56. So don't worry if you were just busy writing a lot of numbers down, because let's go do another problem and hopefully it'll make even more sense. But you've got some pretty good notes there. I'm going to clear my screen because I want to show you the Desmos on this. So I keyed it in. You know what? Let me see if I can go to the live one. All right. So I keyed in. I found somebody's demonstration on Desmos for Eulers and just played around with the numbers. I integrated that derivative that they gave us, and it went through the 0.05. So I created the original function. The Desmos is actually calculating out then the slope, and the orangish line, the gold line, would be the original tangent line built from that 0.05. At what was the first point we recalculated at gave me the second line. The green line is the second version of the tangent approximation, and you can see how that's landing us at 0.8, 3.56. How could I get more accurate? I could increase the number of steps. So if I did that, you can see how, what am I up to? 7, 8 steps, 8 steps, so on. We're getting very, very close now to the actual curve. Now, would that be tedious to do? Oh, absolutely, because I'm at 15 steps. So if you can imagine doing that process 15 times, you can get pretty accurate. All right, back to our problems here. Let's go. Part B, solve the differential equation with the initial condition 0.5 and use the solution to find the 0.8. And let's do it. So this is just a practice on separable differential equations. This looks like it's going to be a nice, easy one. We did this earlier in section 7, or chapter 7. So I'm going to just multiply up by dx because it was already separated. There are no y's in this particular problem. And then we're going to integrate each side. And as I integrate, I'm going to get y equals x to the second divided by 2. So 1/2 x squared minus 2x plus some constant. We bring in the ordered pair 0.5 to find our c. So I get 5 equals 0 minus 0 plus c. Obviously, c is 5. So I get y equals 1/2 x squared minus 2x plus 5. This is what I needed to do for that Desmos. I needed to create the original function so that I could do it. Now it says find the actual value of y of 0.8. And to do that, we'll just key it in. 1/2 0.8 quantity squared minus 2 times 0.8 plus 5. And throwing that in your calculator, trust me on this one, I get y at 0.8 is 3.72, which kind of marries with the fact, we were really getting close at 15 steps, weren't we? But when we were back down at 2 steps, our answer, 3 steps, our answer was 3.65. And we can see that we are under approximating it, right? Since my original function is concave up, if it's concave up, that means my tangent line has to be under the curve. So obviously, my approximation will be an under approximation. Sometimes you have to verify or justify whether it is an over or underestimation. Okay. Part 2, we are going to skip because it has 5 equal subintervals, and I just don't think you need to do that. So let's go do number 3. You'll still get plenty of practice here. Assume that f and f prime have the values given in the table. Use Euler's method with 2 equal steps to approximate f of 2.6. So, and they give us f prime, so I don't have to calculate my own f prime. That's kind of nice. Euler's method with 2 equal steps. That's the part that's kind of throwing me. Oh, I see it. 2 equal steps. We're going from 3 down to 2.8 down to 2.6. Obviously, delta x then is a negative 0.2 on both cases. 2 equal steps. And then I have the derivatives. So let's set up. We have our x, our y, and I have my y old plus the change in x times f prime will give me my y new. Kind of draw a table there. So to lead us off, I have the ordered pair 3, 2. That's my starter value. Then my next x value is going to be coming in at 2.8. And my last one, I'm going to stop when I get to 2.6. My change in x, because I do need to know that up here, my change in x was negative 0.2. So getting it all started, my y old is my beginning y value. I start with 2, and I've got to add to it. Remember, this all represents the change in y that occurs. So I take 0.2, which is negative because we're decreasing in x values, and I multiply it by f prime of 3 here. So we have x. F prime of 3 comes in at 0.4, doesn't it? I kind of want, so I've got 2 plus negative 0.2 times 0.4. And that would calculate out to 2 minus 0.08. I would come in with 1.92. I'm going to change my ink color. And that's going to be a 1.92 now, updating to the next point as we moved over. Now I take my y old, my 1.92, add to it. My delta x is changing at negative 0.2. And I'm going to look at f prime evaluating at 2.8. Which means, I'm going to draw a line to keep these straight. I have 1.92 minus 0.2, f prime at 2.8. F prime at 2.8 is 0.7. So that's 14 with 2 decimals. That's a 0.14 negative. So 1.92 minus 0.14, decreasing it, gets me to a 1.78. There's my updated y value, and that is where I stop. I get 2.6 comma 1.78. So the approximate value, let's answer the question. The approximate value for 2.6 turns out to be 1.78. Kind of nice to do it with tables, because remember how we had to actually calculate out the slope there. I may come back and do an example for our example 2, but I'll do it on another video. So if you want to watch that one, you sure can. All right, the table at the left gives selected values for the derivative of the function g on the interval between negative 1 and 2. If g of negative 1 is negative 2, yep. Oops. Nope, that's not there, is it? It's just given in there. Just so happens that it looked kind of like that, but that was the slope there, given as 2. An Euler's method with a step size of 1.5 is used to approximate g of 2. What's the resulting approximation? All right, let's just kind of set it up the way we always did. X, Y. I like to keep track of these over on the left side. My original starting point was -1, -2. I'm going to do, how many steps? Is used to get to, I need to get to 2. And we have step sizes of 1.5. So if I add 1.5, that'll take me to 0.5. They'll close the parenthesis there, and I got more space, I can tell that. That's going to get me to 0.5. Don't know. I'm going to be calculating that. And then I add another 1.5 because our delta x was defined as 1.5. That 0.5 times 2, or 0.5 plus 1.5 gets me to 2. So it looks like we just have 2 steps to do on this one. Now, what's the process? I take the y old, add to it the change of y, which is a calculation of delta x times f prime of x, which is really your x sub old as well. And that should give us a y new. Okay, I'm just going to draw some lines here. Keep things nice and neat. Y old, start with my y value, add with it my delta x, multiplied by f prime. F prime of -1 turns out to be 2. So 3 minus 2 gives me 1. Give me a second, Joe. So I put 1 in, that's my new y. 1 plus 1.5 for delta x. F prime evaluated at 1. Ooh, it turns out to be 0. That looks funky. Oh, sorry, it was an x value at 0.5. There we go. X at 0.5. So that is not 0, that is 1. 1.5 plus 1 gets me 2.5. That comes down. I now have my ordered pair. When G is 2, I'm going to approximate this to be a y value of 2.5. Okay? That is it, you guys. Hidden Figures, I'd love to play that for you because they use Euler's method in it. And perhaps we will when we Zoom. There is a worksheet that follows, and boy, oh boy, does it have a lot of problems. I think you'll get sick of them real quick. So what I've done in the past is we've done 1, 2, and 6 for practice. That'll be plenty of practice. Have a great day.